2.5 years ago, I told you about a company using death rays to drill deeper into the earth than anyone has before. The goal? Unlock cheaper and more plentiful geothermal energy for the world. Well, I just got back from Houston, Texas, where I watched them do exactly that. They melted through solid granite with millimeter waves in real time. We're not talking lab experiments anymore. This drilling operation could change how we think about geothermal energy. The heat beneath our feet could be the most versatile, reliable, and abundant energy source ever, but it's out of reach for most people. While the old joke goes that nuclear fusion is always just 30 years away, an offshoot of fusion tech may be changing the future of geothermal drilling today. So does this team have what it takes, or is Quaise out of its depth? I'm Matt Ferrell. Welcome to Undecided. This video is brought to you by Incogni. Let me quickly remind you why Quaise is doing what they're doing down at their Texas headquarters. A major obstacle to geothermal is that the hot spots it needs occur near tectonic plates. Basically, the best place to drill for heat is near volcanoes and where the Earth's heat is closest to the surface. Now, outside these areas, even if the heat is conveniently located closer to the surface, the limitation isn't hard rock, it's hard cash. Drilling deep enough to reach really hot temperatures is incredibly expensive. In fact, the drilling process makes up anywhere from 30% to 57% of the cost of establishing a geothermal plant. That's where MIT researcher Paul Waskoff proposed a different approach. He borrowed technology from nuclear fusion research, specifically gyrotrons that generate millimeter waves. Now, millimeter waves are electromagnetic radiation, kind of like the lasers you might associate with spy movies or cat toys, but they're much longer. These high-powered vacuum tubes produce beams that fusion researchers have used to heat plasma for the past 50 years. And by heat plasma, I don't mean leftovers in the microwave. During fusion, plasma reaches over 150 million degrees Celsius. That's about 10 times hotter than the center of the sun. Now, Quaise is adapting this technique for drilling.
So this is, the inner part is a gyrotron itself. Okay. This is a superconducting magnet, and that creates a very strong magnetic field that bunches together the electrons.
Right.
So in the bottom, you've got a filament, and then you're heating this up and it's spitting out electrons.
Okay.
And they pop through this section of the body where the magnetic field is concentrated to group them together. And as they group together, they're giving off electromagnetic waves, which are then bouncing around in here through a series of mirrors and coming out a window. And so then these emit out the window, and then that's what we use, we capture, and we direct for our energy drilling.
So why pivot to pulses? Because grinding through rock is one thing, but vaporizing it is another. It simplifies the process. No drill bits to replace, no temperature constraints, no worry about pressure, and no fussing over rock strength. The drills need all the help they can get. Making geothermal energy viable requires reaching as far down as possible. The closer you are to the Earth's core, the more heat that you feel, with temperatures increasing roughly 25 degrees Celsius per kilometer or 1 degree Fahrenheit per 77 feet. Higher temperatures mean more energy extraction, especially if you can create supercritical steam at around 374 degrees Celsius to turn turbines and generate electricity. So here's what's changed since my last video.
So one of the things that we have to remember is that Quaise was not created to just be a drilling company. We're not in the business of selling or offering drilling services. We are in the business of putting clean energy, firm baseload energy on the grid on a global scale.
That's Carlos Araki, Quaise's CEO, and this represents a fundamental shift in how they're positioning themselves in the market.
So this is the year where we stop talking just about millimeter wave drilling, which is the predominant narrative that you've heard for the last 7 years. And we start talking about our first commercial project under offtake agreement.
Quaise isn't just developing a cool drilling technology, it's becoming an energy company with a concrete timeline and power purchase agreements.
We will confirm the first super hot geothermal resource as soon as the end of 2026. We have leases, we are well underway in PPA negotiations, and we will put the first electrons on the grid in the 2028 to 30 timeframe.
That covers the business side, but what do these death rays actually look like? Side note, they don't like me calling them death rays, but I just can't help myself. But before we drill down on the details of what I saw in Houston, let's take a quick pause. While Quaise is working to keep their drilling operations secure, your personal data might not be as protected. It's kind of shocking how easy it is to find your personal details online. Well, today's sponsor, Incogni, can help get to the source of the problem and restore some of your privacy. Data brokers make a business out of collecting your personal details and selling access to it. And sometimes they sell your info to some pretty shady people. Incogni can help with this. We have the right to request that data brokers delete our information, but it takes a lot of time, effort, and sometimes legal action. I signed up for Incogni, gave them the legal right to work on my behalf, and then just sat back and relaxed. They also just launched a brand new tool called Custom Removals for subscribers to their unlimited plan that's really cool. It allows you to flag an unlimited number of sites where your data is exposed. It could be easier. If you want to take back some of the control around who has access to your personal information, give Incogni a try. Take your personal data back with Incogni. Use code Undecided at the link below and get 60% off an annual plan. Thanks to Incogni and to all of you for supporting the channel. All right, now let's get back to those definitely not death rays. Well, I got to see their full-scale demonstration at a neighbor's drilling facility outside of Houston, Texas. But hold on, safety first.
3 points of contact, one hand on the railing, 2 feet on the stairs. You limit your ability to fall backwards or forwards walking downstairs.
After the safety briefing, because this is real industrial equipment, I got to see something pretty incredible. This is a full-scale drilling rig, but instead of a traditional drill bit, they've integrated their millimeter wave system. The key innovation is this articulated waveguide that can move up and down while transmitting power. It does exactly what it sounds like, contains and guides the millimeter waves into that nice, well, death ray.
So really 3 things that we had to develop to enable millimeter wave drilling. So one of that is the ability to move and shoot millimeter wave at the same time. So in the fusion industry, the gyrotron and waveguide is always stationary. What Quaise had to do is design what we call a trickling waveguide, a dynamic waveguide, a waveguide that allows us to stroke while we're sending power through it.
Next is the integrated diagnostics like radar to assess the rock's depth and a pyrometer to determine the rock's temperature. This helps maintain consistent measurements as the drill moves deeper into the earth. The team also has developed a special bottom hole assembly that shapes the beam.
We basically beam the power through the tubulars in a very Gaussian type of shape. But when we get to the bottom, we actually want to fan out that beam such that it burns a very uniform circle. So we actually do a conversion downhole that actually converts that into a very circular beam.
By fanning out the beam, they're making a larger diameter than the assembly drilling the hole. The result? A perfectly circular hole through solid granite with room to spare for the waveguide pipe being lowered into the hole. And if you're wondering how you get all that vaporized rock back out, it's with air combined with that extra space in the well. Traditional drilling uses high-density drilling mud to counter surrounding pressure and prevent well collapse. But millimeter waves don't require drilling mud because of how they strike the bore walls, causing vitrification. It transforms the surface into that glassy coating. This seals wall cracks and increases internal pressure, balancing the outer forces. The result? Deeper, more stable boreholes without any drilling mud, making the whole process more profitable. To evacuate the tiny vaporized rock particles, air is blown through the waveguide, carrying the waste up and out of the well. The hot exhaust is then filtered through water to cool it down and collect the waste material. The waste can be easily collected and cleaned out, allowing the water to be reused again and again. But the most impressive part is what I got to see and hold.
I will say it never gets old to make lava at work. But we've gone through a number of different drilling parameters to perfect this recipe and to make sure that we can drill this reliably.
And these are rock solid results. They're actual rock samples they've drilled through. You can see the glassy liner that forms as the rock melts and solidifies, essentially creating its own casing. But drilling through different types of rock presents different challenges. The Quaise team has learned through experience that rock composition significantly affects the drilling rates. Granite contains quartz, which reflects millimeter waves more than other minerals, requiring more energy to reach vaporization temperatures. Basalt, being more homogeneous, may allow for faster drilling rates. It's a complicated science that's still getting figured out. And getting to the bottom of the geology matters because in real-world conditions, the Quaise team will encounter all sorts of variation in the rock that could affect their drilling efficiency. There's another problem that could drill down into their success though, and lab testing can't fully address it. If groundwater continuously seeps into the borehole, it could get Quaise into hot water, literally. It would take enormous amounts of Gyrotron's energy just to boil it away, dramatically increasing drilling time and energy costs. But their test drill sites should help answer that question. The power requirements are also substantial. The Gyrotron pulls incredible energy, requiring custom-built power supply systems that may exceed what the electrical grid can provide at the drilling sites.
This is a 100 kilowatt system. 100 kilowatts is probably the power of a car, probably a car you drove in here today. We need to upgrade that to a megawatt. megawatt is like a small jet engine. We have that gyrotron coming next month.
All of this equipment needs to be containerized and transportable to remote drilling sites, adding complexity and cost. That said, the progress since my last video has been dramatic. They started with a klystron, which is another vacuum tube that generates microwaves, but have since moved up to successfully drilling 10-foot holes with their gyrotron.
This was drilled with a klystron. So the klystron, the power output was about 10 kilowatts there. That was at a lower frequency using a different mode. And so it was important that then we got our gyrotron in the correct operating frequency, and we also got higher power. We were able to get a 100 kilowatt output gyrotron. Higher power enabled a bigger hole, and the higher frequency really enabled us to go deeper as well.
And Quaise isn't stopping there. I also got to see where they're setting up their 1 megawatt system, although I missed the actual setup by probably a matter of weeks. And the scale difference is massive.
The gyrotron's gonna sit in that because it needs to be in 1 megawatt, it needs to be immersed in oil. Part of it has to be immersed in oil.
Why is that?
It has to, it's with keeping it cool, but then also preventing breakdown. So you have a dielectric oil in there because everything's under such high voltage that you can have arcs in the air.
To me, one of the most fascinating aspects of this story is the relationship between Quaise and the fusion industry. The fusion industry was initially skeptical that gyrotrons could work for drilling. These are incredibly delicate machines designed for precise laboratory conditions and controlled fusion reactions. But by adapting them for the harsh, dirty environment of drilling operations, Quaise is pushing this technology far beyond what the fusion industry thought was possible. They're basically improving gyrotron reliability, and this cross-pollination is really heating up both industries. Now, all those improvements will eventually flow back to help with the fusion industry when fusion energy finally becomes commercially viable. And this is exactly why I love following cutting-edge technology. Innovation doesn't happen in a straight line. Sometimes the perspective you need comes from a completely different industry tackling a very different problem. Now, fusion researchers, aside from MIT's Paul Waskoff, probably never imagined their plasma heating technology would end up drilling holes in the ground. But here we are, and both industries are better for it. But here's the critical question. Can this actually compete on cost? Let's dig deeper into the numbers. Well, according to recent data, onshore wind can produce electricity for as low as $30 per megawatt hour, and solar is similarly competitive. Nuclear power typically runs around $100 to $150 per megawatt hour. Quaise estimates their technology could achieve costs between $68 and $115 per megawatt hour, depending on the location and depth required. And that puts them potentially competitive with nuclear, but still significantly higher than wind and solar. However, Carlos explains something crucial about why this approach could actually work at scale.
You have to remember, oil and gas powers the world today. Those projects will command, if we use internal rate of returns metric, of 15 to 30% annualized. You know, wind, solar projects, 5 to 10%.
Okay.
So when you bring into the world a geothermal project that has those metrics and that scalability potential, you've bent the curve on energy transition.
As Carlos says, offering clean energy isn't enough. You need to show profitability so that the oil and gas industry will want to follow suit. It's all about the internal rate of return.
It's only when you bring the IRRs up to the 15, 20, 25, 30% that it's inevitable.
That's the super hot rock that you have to get down to.
It's the only way to get there. It's the only way to get there. Remember, I told you wind and solar is 5 to 10%. We're not even close.
And going hot means accessing what they call super hot rock, or temperatures above 375 degrees Celsius, where you get supercritical water that's much more energy dense. A well plunging into super hot rock could yield up to 10 times more energy than a conventional enhanced geothermal system. Research indicates that super hot rock could reduce geothermal's levelized cost of electricity by 50% and have a lower cost than onshore wind or even solar. The heat beneath our feet is staggering. Even 0.1% of the Earth's stored heat could, in principle, cover humanity's total energy appetite for millions of years. Yet despite that vast resource, geothermal plants generated just 0.3% of global electricity in 2018. Recent IEA modeling shows that with next-generation drilling and reservoir technology, geothermal could realistically provide up to 6,000 terawatt hours per year by 2050, which is roughly 15% of the additional electricity the world will need. One thing that impressed me was how much of this technology leverages existing infrastructure and expertise.
We designed it to be exactly the same, so it'll be as compatible with conventional drilling as possible.
Operators could very easily be retrained to do this system.
Absolutely.
So
yep.
Transferable skills from...
There's nothing to it. Yeah, it's just connecting drill pipe.
The drilling process itself is remarkably simple compared to conventional drilling. And when Waskoff estimated the cost originally, he found that for a hole that was 20 centimeters or about 8 inches in diameter at about 10 kilometers deep, it would cost something like $500,000 of electricity to vaporize the granite, compared to around $30 million for a mechanical drill. He estimated that the gyrotron system could be maybe 10 times cheaper than a really deep mechanical drill well.
10 days is 240 hours, so 30 hours, an eighth of the time drilling, and the other 7/8 of the time running the pipe in and out of the hole to replace that drill bit. We talk about drilling a very consistent 5 meter per hour rate. It just goes because there's nothing to replace it.
According to the US Department of Energy's 2019 GeoVision report, leveraging these untapped subterranean heat sources could increase geothermal-based electricity 26-fold by 2050. So where does this go from here? Well, Carlos laid out a clear timeline.
So we will raise $200 million this year. So we'll launch that Series B this year. We will use the proceeds from that Series B to create that first geothermal project. And importantly, we'll do it as a commercial project. It's not a demonstration. It's not a proof point. It is a product, electrons, for somebody that's paying for them.
The first project will likely be Oregon, with other sites in development across the western US.
From today's perspective, it's not definitive that it's going to be Oregon, but I think it's 90% likely that it will be Oregon.
Okay. But Carlos's final message was more than just about quays.
Energy transition is solvable, but we have to stop being shy about pursuing the real solutions at scale. This is a hard problem. There are solutions. Deep geothermal, super hot geothermal is one of them. I think fission could be one of them, and fusion certainly can be one of them.
Right.
And that's that. Those are hard. Let's not shy away from that. Let's embrace them fully, because that's the path forward.
Look, I don't know if quays will achieve everything they're promising, but what I do know is that in the 2.5 years since my last video, they've gone from melting small rock samples in a lab to operating a full-scale drilling rig and signing commercial agreements. That's the kind of tangible progress that gives me hope. If they can make geothermal economically competitive with oil and gas, the future of clean energy could really be heating up. Who knows how much further this could look up? Or should I say, how much deeper things could go? But what do you think? Are you convinced that this technology can scale? Or do you think there are just still too many unknowns? Jump into the comments and let me know. And if you want to drill deeper into the story, I've got an extended version over on Patreon with more of those famous 20-kilometer holes that Quays has talked about in the past. If you'd like to join, the link's in the description. And be sure to listen to my follow-up podcast, Still to Be Determined, where we'll keep this conversation going. Keep your mind open, stay curious, and I'll see you in the next one.